All right, hello class. Welcome back to lecture 9. So up till now, in lectures 1 through 8, we have, for the most part, just been building up the mathematical machinery necessary to solve the optimal control problem. That's not to say that the results that we've gone through heretofore are not useful in themselves for analysis or even for control in the open loop, for example, or for pole placement. But that wasn't the real goal of what we've been doing so far. The real goal has been to prepare for essentially lectures 9, 10, 11, and then, of course, the stuff on robust control. Now, this lecture itself is rather short. 13 slides, I think, I have it at. And that's not because it's not a significant result. It's just that we've built up enough mathematical machinery and notation that we can efficiently present the results without much ado. And in particular, I'm not even going to post discussion points on this lecture because really there are no new concepts that we're going through. We're just putting together the pieces of the puzzle that we've already laid out and use them to do controls, optimal control. Now, that's not to say that this is the sort of ultimate lecture, in that we're not covering, in this lecture, we'll cover that in the next lecture, optimal dynamic output feedback control, which is really what we want to do. We're going to cover the full state feedback control. And here it is, full state feedback control, with the emphasis on the full state. That means we have available to us measurements of every state in the state space representation. Now, the book will go through and do this. This lecture is in the book. And the book will also actually cover Hinfinity optimal estimation. Hinfinity optimal estimation is not a topic. It's not a lecture in this course. For the simple reason that we have something better. We have dynamic output feedback control, which is truly optimal. Optimal estimators coupled with optimal controllers are not optimal. So we're not actually going to devote a lecture to that, and we'll just do the full state feedback rather quickly. Because in reality, of course, dynamic output feedback control is more useful, although it's a little bit harder. And so the results in this lecture will sort of get us prepared for the dynamic output feedback control, but it's not the final result in and of itself. All right. So having stated that, right, let me formulate the problem with 2 slides. So remember, in the previous lecture, we have allowed ourselves to formulate whatever optimal control problem we have as the feedback interconnection of the 2 input, 2 output nominal or plant, where these are our regulated outputs and these are our sensed outputs, and these are our exogenous inputs, and these are our controlled inputs. Right. And we have 2 possible choices for representation of that nominal or that plant to be controlled. One is the transfer function / system representation, so the for system representation, which gives you the individual maps from each of those inputs to each of those outputs. And the other one, if you manage to construct it, is the 9 matrix representation. Right. So that's what we're starting with. And then our variable is the controller. That's what we're looking for. Where the controller itself can be parameterized as a system, or a transfer function, or it can be parameterized as a 4 matrix state space system. Right. So our goal is to choose AK, BK, CK, and DK, such that the map from the exogenous inputs, the closed loop map from the exogenous inputs to regulated output is minimized in the H infinity sense. Minimize the H infinity norm of that map, of that closed loop system. And remember, the closed loop system is represented as the lower star product, which is the interconnection of P and K. Right. So that's the full problem, the dynamic output feedback problem. So then what is the state feedback problem, the full state feedback problem? Well, remember that the dynamic output feedback problem is hard. We have a state space representation for the dynamic output feedback problem, right, where our variables are dk, bk, ak, ck, and dk shows up here as well. It shows up here, here. And anyway, the whole thing is horribly nonlinear and non-convex in our decision variables at this point. And so a much easier problem to handle, which is also non-convex, but we can easily convexify it, is to simplify our controller by getting rid of three of those matrices, the AK, BK, and the CK, and only searching for the static map. Remember, this maps U of t equals dk y of t. So just look for that one matrix dk. So that's the static feedback problem. Of course, what we've stated in previous lectures, however, is this is the static output feedback problem. So it's not, and we've argued, of course, that the static output feedback problem is NP-hard, is very intractable. Static output feedback problem. Right, so what is one to do in this case? Well, of course, if we're now searching for a controller where these three AK, BK, and CK are 0, and we'll just substitute in dk equals f to make our notation a little bit simpler. Right, we can't solve this problem unless we make some certain restrictions on the plant as well, right? Because we can't solve the output feedback problem. So what are we going to do? Well, in this case, we have to constrain ourselves or limit ourselves to the case where the output is the state of the system itself. So y of t is simply x of t. So if we think of y of t in sort of the full plant mode, right? That's cx of t plus d to 1 w of t plus d to u of t. Well, we can't have either of those terms if we're just looking for x. And of course, we can't have c. Well, we have c, but it's just the identity matrix. And so we have to restrict ourselves to plants that have this particular structure. We don't put any constraints on these other matrices. They're fine, whatever you choose them to be. But we do restrict this last set of matrices here to be first identity, and then these D matrices just to be 0. That's C2. Right. So this actually is rather easy in the state space representation, as I mentioned. We're already on slide 4 of 13. It's much harder in the system transfer function representation, where the difference between state feedback and output feedback is not so clear cut, right? So we're going to just cross off this system representation and work only in the state space representation. All right, so how do we do that? Right, so first of all, we form the feedback interconnection. So if we took this like big horrible thing right here, and we plugged in, this is 0, 0, 0, 0, C2 is identity, C2 is identity, 0. A lot of things are 0 here, right? So 0, 0, 0. So everything here is 0. We only have this term left. We have this term left. What do we have over here? Well, dk is f, so we keep that. But let's see, what else do we get? So most of those terms disappear. Most of those terms disappear. D22 is 0, so the q is just identity. So this big, nasty, horrible state space representation simplifies out to a very simple structure, right? Where k here is 0, 0, 0, f. And p had the structure we had on the previous slide. So when that happens, right, the closed loop state space matrices simplify, and this is of course the map from W to Z, right? Simplify to a state space form which is A plus B2F, C1 plus D12F, and then these don't have any variables at all, right? So we see now that this is much simpler because F appears linearly in the closed loop state space representation. Let's change our color. Right, okay, so that's pretty encouraging. Okay, so now we have a representation which is linear in F. Now how do we enforce the H-infinity norm gain bound, right? How do we minimize the H-infinity norm of that closed loop system? Well, as you remember, norms are convex in your function. However, optimizing that norm is a bit tricky. And so, in particular, if we apply the Schur complement, the KYP lemma to the system, or at least the KYP lemma from lecture 7. And I believe you can just recall the KYP lemma from lecture 7. Well, what has changed here? The only thing that's changed is A has become A plus B. A plus B2F. C has become C plus D12F, I believe. D is D11, and B is B1. I believe that's right. Yes. So we just plug in those values to into the Schur complement. This is C1, I believe. Yeah. So we plug those values in for A, and for B, and for C, where's C, and for D, and we get the expression, or the not LMI, right here. Right. So this part of it looks familiar because this is the bit we did for stabilization, right? This is the LMI for stabilization. So we're on track to get something reasonable. However, so that's bilinear in these two variables. We can do the variable substitution. However, right, we've also got this f appearing here. So we can't, that f does not means that it's going to be hard to do the variable substitution because we have to eliminate all versions of the original variable, which was f. And if f just appears by itself, that's going to be hard to do. So there's our variables here. Those are the variables. So it's nonlinear, it's quadratic. So we can't directly apply the variable substitution trick. So we need a first step. And the first step is to note that this looks suspiciously like something we'd seen in the Schur complement. Right? So in particular, if we go on to a previous slide, if you remember the Schur complement, right, it has this, this term which doesn't get touched, which goes straight here to this matrix here. It also has this quadratic form, right, where the R's become linear in R, and this Q matrix goes over here. And so this is, the Schur complement is a way of eliminating linearities in each of these bilinearities in each of these terms, so that if the variable only appears linear in each of those, we can do optimization. So now if we apply this this trick to the KYP lemma, right? So here's the KYP lemma without the controller, of course. Well, let's look at this. Well, the nominal term, right, in the Schur complement is just m. That's this bit right here. The R is this bit right here. The R transpose is this bit right here. And we'd actually like to also get rid of this 1 over gamma, because that's obviously not convex in gamma. And so the Q term will be just identity matrix, but times 1 over gamma. And also we put a negative sign in there. So that now when we apply the Schur complement to it, we get that this term is going to go here. Well, we get a bigger LMI, where there's m, which goes here. This R goes here to R transpose. This R transpose goes here. And this Q just shows up here as the inverse of Q. And the inverse of the identity is just identity. And the inverse of 1 over gamma is just gamma. So we get negative gamma I here. Okay. So right now we apply this. So if we apply the Schur complement to the KYP lemma now, we get a new version of the KYP lemma. Where the problem is bigger. So dilated means we've increased the size of the LMI. But the terms are simpler. It's linear in gamma, and as we'll find out, it's convenient for controller synthesis as well. So if we now plug in A plus BF here, right, for the A matrix, and we plug in our version of C here, right, that shows up there and there, and B1, B becomes, it's just B1, and D is just D11. Right. So we've got a condition for full state feedback, which is close to what we need, right? It's still bilinear in F and X. And we still have this problem that F doesn't multiply X, so we're going to have trouble getting rid of our variable substitution entirely. However, we know that from stabilization that there's one more step we need to take, which is, we have the problem that between X and F there's a B. Right? There's this term B here. So if we take these two bits right here, we have a term that looks like X B2 F, right? So the X and the F don't multiply, so we can't do the variable substitution quite yet. Now, as we noticed in of course, stabilization, right, there's a dual version of the Lyapunov inequality, and so the question is there also a dual version of the KYP lemma? Okay. On these notes, I just give a dilated version of the KYP lemma for reference, because this is independently helpful and useful. In fact, actually, most people typically start with the dilated version of the KYP lemma, but we didn't because we didn't need it quite yet. But now we do, right? So mostly going forward, we're going to be working with the dilated KYP lemma, so a larger version of the KYP lemma, which is more linear in variable gamma, for example. Okay. But like I said, it's not quite the form we want, because the K and the X don't directly multiply. And so we need to, as for stabilization, find a dual version of the KYP lemma. So there is such a dual, right? And derivation of it is relatively straightforward. It's one slide on the next slide. But I'll just state what it is, right? So for comparison between this and this, right? If we just look at these two in sequence, right? There's two main differences. The first, of course, as for the dual Lyapunov inequality, right? A gets swapped with A transpose. The second change is a little bit more subtle in that the y variable gets moved over to the x, or the x variable gets moved over. So the x variable, which was originally multiplying b, now gets moved over next to c. Right. So this x gets moved from b over to c. And also everything gets transposed as well, right? So b transpose becomes, well, actually that doesn't change. So actually that doesn't change. So now if we, so that will be useful, right? Because now by moving the x over to the c, we'll be able to do a variable substitution. But I'm getting ahead of myself a little bit. So the verification of the dual KYP lemma, again, follows in a straightforward manner from the dual Lyapunov equation. And that's relatively straightforward because, right, the 1-1 block of the KYP lemma is the Lyapunov inequality. Right? The 1-1 block, right, of both of these cases is the KYP lemma. So, is the Lyapunov inequality, right? So it makes sense that we should be able to approach the problem the same way we did for the Lyapunov inequality. And if you remember what that was, well, what did we do? We multiplied the left and the right of the Lyapunov inequality by x inverse, right? And declared x inverse to be our new variable and constructed things that way. So we'll do the same for the Lyapunov, or for the KYP lemma now. So we actually go it a little bit backwards. We're going to start with the dual version and show that that implies the primal version. So this is sufficiency. So suppose that suppose the dual LMI is feasible. Right? That is, there exists a y greater than 0 such that this is less than 0. Step 1. Step 2, define the variable x, right, as a potential solution to the primal KYP lemma. Right. And then we will show that the x solves the primal KYP lemma, and therefore shows that the H infinity norm of this system is stable. So how do we show that? Right? Well, if this is negative definite, we can multiply on the left and the right by a full rank matrix, which is also symmetric, and positivity will be preserved. So if we multiply on the left and the right by this matrix, well, this y cancels that y, this y cancels that y, this one cancels this one cancels this one. The y doesn't appear in these two blocks here, but y inverse does come over here and show up on the left and the right of b. However, of course, we know what y inverse is. We've called it x, right? And so that's okay. We can have x there. So y inverse also shows up here and shows up here as well. And so we have that y inverse showing up several places, which is actually now recalled x. Right? Shows up there, shows up there. And so this Lyapunov, or this LMI is satisfied, which is the KYP lemma in the primal version. So because there exists a solution to the LMI for the primal KYP lemma, we can conclude, well, it's the dilated version anyway. This is the original version. We can conclude that our system has H infinity norm less than gamma. Right? So that's the one direction. And these steps can be reversed. I don't think I actually do that. So how would you reverse the steps? Well, suppose that the H infinity norm of the system is less than gamma, step 1. Then there exists an x such that this is satisfied. Here I should do a new color because we're going the opposite direction. There we go. Step 1. Step 2, this is satisfied. Step 3, this is satisfied. Now multiply on the left and the right by x inverse. So let step 4, let y equals x inverse. Multiply on the left and the right by x inverse. That's step 5. And then we get that multiplying on the left and the right equals this, step 6. And because the original LMI was negative definite, step 6 is also negative definite. And therefore, the dual KYP Lemma is necessary and sufficient for the H-infinity norm of the system to be less than gamma. Right. So again, nothing fancy there. We're just using the same tricks, dualization tricks that we used for stabilization. We're just using it for a larger matrix. So now we have that we can apply this using a variable substitution trick. Apply this dual KYP lemma by plugging in here for A, right? A is now A plus B to, I think we're calling it F. Y is, or C goes to C1 plus D 1 to F. B is B1. D is D11. It's B1. And then we get this all new version of the controller synthesis condition where F multiplies Y. And furthermore, C1 plus D1 to F, F multiplies Y over here as well, so that when we do our variable substitution, we can eliminate F entirely from the condition. Right. And we use that on the next slide to show that this LMI is necessary and sufficient for there to exist a full state feedback controller whose closed loop H-infinity norm is less than gamma. Okay. So remember, this is P here, right? This is the nominal plant. Remember, we're doing full state feedback so that the out Y is just X. And this is the structure of a controller where we've made those three terms 0 and we only have F. Right? So what's the proof of this? Again, it's a straightforward application of the dual KYP lemma and the variable substitution trick. So how does that work? Well, there's nothing fancy about it. So let's go through it real quick. Suppose there exists an F such that this closed loop norm is less than gamma. Now here I use some like weird notation just to avoid like crowding the slide a little bit. That this was the expression from the previous slide. That's a closed loop system. So suppose there exists an F such that that's true. Well, by the dual KYP lemma, right, we just apply the dual KYP lemma to a closed loop system. There's our C's. Well, then this must be satisfied, right? This inequality must be satisfied by the dual KYP lemma. Okay, so if that's satisfied, well, let's propose a solution to the LMI that we're proving now. So propose step 2, propose a variable z, which is this, and we keep our original y greater than 0. Okay. So we look at the LMI that we're trying to prove stability of, right? And then we plug in for z here. Z goes there. Z goes there. Z goes there. And z goes there. Right? So we plug in those values of z, which are fy. That becomes that, and that. So okay, now what? Now we just factor things out, and so we get y times this, y times that, y times that, y times that, and by step 1, right? We know that this is 0, and so this LMI is feasible. Right? So by the KYP lemma, we know this is less than 0, and these three matrices are equal, and so that this matrix, the one we're trying to prove, is feasible. So we now have 1 implies 2. For the converse, suppose that this LMI is feasible. This is our variable substitution, of course. For the converse, suppose that LMI is feasible. So this is 2 implies 1. Suppose this LMI is feasible for some y greater than 0 and z. Define a feedback controller in this way, right? As the sort of the counter to the variable substitution, the inverse of the variable substitution. And then we show that the KYP lemma applied to this closed loop system right? When you plug in those values, is negative definite. And how do we do that? Right? Well, we look at it, right? So we've got these Fy terms here. They show up here, 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 and here. But Fy is by definition z, right? Because you can, if f equals zy inverse, then z equals Fy, just by multiplying both sides by y. And so that becomes z there, that becomes z there, that becomes z there, that becomes z there. And f doesn't appear here anymore, and so we can conclude that this inequality is satisfied. Right? So that proves, right, that the KYP lemma, when applied to the closed loop system, is negative definite, which implies that the H infinity norm of the closed loop system is less than gamma. Right? So we started with feasibility of this right here, which is of course the same as this, and we worked through to show that this is satisfied, and therefore by the KYP lemma, the H infinity norm is less than gamma. So again, no new machinery introduced here. This is a straightforward application of KYP lemma, the Schur complement. Of course, we also have the closed loop system representation. The Schur complement, duality, and variable substitution. So we introduced no new tricks in this lecture, right? KYP lemma comes from lecture 7. Schur complement, that's pretty ancient. Variable substitution and duality come from, I forget, it was lecture maybe 5, I forget. And the closed loop system representation comes from lecture 8. So again, we've just taken the pieces of the puzzle that we've laid out in advance and applied them to the full state feedback synthesis problem, where we assume that the output is full state, we have access to measurements of all the states, and the controller has a specific structure where it has no dynamics, it has just a direct feed-through term, so that u of t is f y of t, and y of t is just x of t, so that's equal to f x of t. Okay. So we showed that this optimal control problem in the H infinity norm can be represented equivalently by an LMI in two variables, y and z, where y is positive and z is indefinite. Z is not even square necessarily. And we can, here's that LMI. And to make y greater than 0, we just put a negative y is less than 0, just to put this all in a single LMI for no good reason. Once you solve this LMI, you can construct the optimal state feedback controller using your variables z and y. Because y is positive, it's invertible, and so we just constructed f equals zy inverse. So we've solved now relatively directly the Hinfinity full state feedback optimal control problem. Done. Next lecture, we will talk about output feedback, dynamic output feedback, where the problem is a little bit more complicated, right? Because we have 3 more variables, and so obviously these variable substitution tricks are going to have to be much more sophisticated. But at this point, we can at least say something about optimal control. And in the next lecture, we'll show that, in fact, the real optimal control problem, not just where you have a plant coupled with an optimal controller, coupled with an optimal estimator, as they do in the book. That's the estimator. Sorry, actually, it's the wrong direction. Optimal estimator, optimal controller. Instead of combining those, we can actually solve this problem directly, combining these into a single block parameterized by 4 matrices AK, BK, CK, DK. Remember that the optimal estimator actually only has 1 variable. Remember, it was L, and the optimal controller only had 1 variable, K. So obviously now we have 4 variables, and so the machinery required is a little bit more difficult, but of course the result will be a much more optimal controller, a much more robust and hopefully useful controller. But anyway, that's something we will address in the next lecture, and I'll end this relatively short interlude before we get to that rather long lecture in lecture 10.